Hi everyone. In this video I want to discuss the third law of thermodynamics. We had already discussed the second law in the previous video. The third law of thermodynamics will help us understand a little bit better standard entropy, and we are going to use standard entropy at the end of this video to solve this problem for the delta S naught of the reaction. Last thing before I move on is that I'm using a new headphone and microphone. Hopefully this improves, or at least has just as good a sound quality as the other videos. Let me give you the definition of the third law of thermodynamics. It says that the entropy of a perfect crystal at absolute zero is temperature equals 0 degrees Kelvin. The entropy of a perfect crystal at absolute zero is 0. What are the units of entropy? Joules per Kelvin. What this means is that the system has only one minimum energy state. Do you remember the equation S equals K ln of W? The Boltzmann equation, right? And then ln of that one microstate equals 0. I'll just put that off to the side. Ln of 1 equals 0. Okay. Now this actually is very useful in explaining the absolute entropy, because we understand that the delta S equals the S final minus S initial. But if the S initial is at 0 degrees Kelvin, then delta S equals the S of the final. What that means is that the third law makes it possible. Why am I off? Okay. The third law makes it possible to experimentally, via extrapolation, get what's called the absolute entropy. Delta, or not delta, but just S. And we'll say standard. This means that it is at 1 atm. These are true values. The S of the system. If you think about enthalpy, for instance, enthalpy formation, those are not absolute. Those are based off of a reference point. are derived using an arbitrary reference. Okay, what this means is that, again, if we start with the initial at absolute 0, then the delta S equals the S of the final. And these are the values in tables. And the entropy of those individual molecules are going to be joules per Kelvin. I think that's it. These are, these tables. These are tables of, again, standard entropies. And we are going to do a problem using those standard entropies, if I could find it. Oh, here it is. Right, it's this problem right here, S naught. Is there anything else I want to say before moving on to that problem of standard entropies? Usually, standard means, again, it's at 1 atm, and usually measured at 25 degrees Celsius. Okay, let us jump into that problem. Real easy. We're going to add up all the entropies for the products minus all the entropies of the reactants. Just make sure that you account for the coefficient, and I should give you the formal equation, and then we'll get to the problem. Delta S naught of the reaction equals, you've seen this before with delta H, the sum of the entropies of the products minus the summation of the entropies of the reactants, making sure that you account for the coefficients. You have to multiply by the coefficient. This is a good illustration of what we mean by absolute versus values that are from an arbitrary reference. If you recall the delta H of reaction, it was a summation of the delta H of the formations of the products minus the reactants. There was a delta here for enthalpy. In this case, there's no delta. It's the absolute entropy, the true value. Now we're ready to look at the problem using this equation right here. Do you want to give it a shot before you see how I would work this? You have a reaction, and you're given the standard entropies. Why don't you give this a go before looking at my answer? Okay, real simple. You have the products. You have to multiply by the coefficient, 193.0. That's the only product, minus. Then we have N2, 1 times 191.5, summation of all the entropies for the products. We have 3 times 131.0, and let me put up square brackets. Make sure that we're minusing all of this. Some students like to have one column of just the products, one column just the reactants, and then you do the subtraction, which is not a bad idea. I just do this out of habit. Okay. 2 times 193, 386. In this case, I normally don't like to rewrite every step, but in this case I will. 191.5 plus 3 times 131. So I have a minus, and this is positive, 584.5. 386 minus that answer, hopefully it's negative, 198.5. 198.5, and it is a negative. Don't forget your units. And that is the entropy for the reaction. What can we say from this result? We could say that the reaction got more very interesting. Is that real? It got less, oh yeah it is, it got less disordered. Got less disordered because delta S is negative. You notice that we went from 4 moles of gas. So this was predictable that it should have been negative because we went from 4 moles of gas to 2 moles of gas. We're actually losing disorder. Or we're getting less chaotic because there's less moles of gas. But let's say losing disorder. Okay, pretty simple. We're starting to do calculations in this unit. The next couple of videos we'll be working with, again, standard entropies, numbers. It's a little bit less conceptual and more computational in the next couple of videos.